what is complex analysis? Complex analysis is basically a branch of mathematical analysis that involves the investigation the investigation of a function of a complex number. Okay, so basically the complex number turns a difficult problems, real problem, into a simple, elegant solvers. Got it. So basically complex what makes the complex variable method special is they often turn the difficult problems in a very simple ones. And if we talk about the application point of view, they are used in evaluating the real integrals. So many difficult real integrals become easy using a contour integration and the residue theorem. All these things we'll see in detail in the complex analysis. So first, just want some application of the integral, some application of the complex number. So yeah, they are used to evaluate the real integrals like this. So in case of a real calculus, it's very difficult, whereas we can evaluate this contour integral in the complex plane. Basically here x square plus 1 is 0, so x is equal to plus minus 1 can be used as a pole. So they are widely used in the engineering, mathematics and quantum physics. Similarly, in fluid dynamics also complex functions are used that describe the 2D potential flow. Okay, they describe the 2D potential flow. So they can be represented as a velocity potential plus stream function. The combined information is given like this. So and we use the conformal mapping as well. So conformal mapping transform the complicated geometry into a simple ones. They are used in the flow around a cylinder or aerofoil analysis. Similarly, if talk about the application in electromagnetism and electrostatics, the solution to the Laplace equation can be represented using an analytical function, and then the electric field lines convert into streams. Similarly, equipotential lines are the orthogonal curves. Okay, so we can use the this complex analysis function to solve the problems of electromagnetism and electrostatics. They're widely used in they're widely used in the field visualization or the capacitor design or solving the boundary value problem of the electromagnetism and electrostatics. Similarly, they are used in the signal processing. So in signal processing, the complex analysis involves the Fourier transform, Laplace transform and many other transform functions. They have the zeros and the poles that determine the system behavior using the stability, resonance, frequency response, that are widely used in the communication system, control theory and obviously in electrical engineering. Similarly, we have the conformal mapping. So conformal mapping is basically a transform a complicated geometry or domain into a simple ones. Okay, the irregular boundary, we have any irregular boundaries there that convert into a simple unit circle. So they are used in solving the potential, they are used solving the partial differential equation and the boundary value problem. There are also complex analysis of complex numbers also used in the number theory. We'll see in detail when we start the complex analysis. So they are used in the number theory as well in solving the advanced number theory problem like the distribution of prime numbers, then Riemann zeta function. Okay, we'll see all things in detail when we start the complex analysis. So before starting with the complex analysis, let's first discuss about the complex number. So this is important things. First we study about the complex number. So what is complex number? So when was the complex? So basically, if you talk with the complex number, so any number z, so it's any number z, they are represented by z, that can be expressed in the form of z is equal to a plus ib, where obviously a comma b belongs to the real number, whereas I is something root minus 1 or iota is I square is equal to minus 1. So this z is called a complex number with a and b are the real numbers. So if you talk about the complex number are first encountered. So in the beginning, let's say you start in the high school, no? When you start solving the quadratic equation, you first encountered in solving a quadratic equation. Let's say x square plus 1 is equal to 0. If you want to solve the quadratic equation of x square plus 1 0, or let's say you want to solve any x square plus 2x plus 5 is equal to 0. If we talk about the solution, so we first check the discriminant. So discriminant is b square minus 4ac. Clearly discriminant is negative. Since the discriminant is negative, its roots are the imaginary roots. Okay, that is the first time we encountered a complex number, because these roots are imaginary number is the part of a complex number. So we have been dealing real number throughout the beginning, from class 1 onward, but once we are solving this equation, this such kind of equation where the discriminant is negative, then we encounter the imaginary number. So the imaginary number becomes the first time we encounter the complex number. So if you talk about the little bit history of the complex number, so the beginning of the complex number is found basically in the work of the mathematician, that is Girolamo Cardano, okay, in the 1501 to 1576. So how he encountered this one? So basically he was resolving a problem to solve the reduced cubic equation of the form x cube plus ax is equals to b, where a is greater than 0 and b greater than 0. Okay. Obviously others mathematicians have later improved on the notation and mechanics of the complex algebra. So it was first encountered in his book that is called the Ars Magna. Okay, so and that start to the use of nowadays what we study the complex number. It started from the mathematician Girolamo Cardano, and it was the work with the complex number, or the work was first found in his book Ars Magna. Okay, so what is complex number? So we can say complex number is a set of complex number is denoted by z, such that z is equals to a plus ib, where a comma b is a real number and I square is equal to minus 1. Okay, so this is the notation we use. So here if you talk about the z is equal to a plus ib, here both a and b are real numbers, and they are two independent real. That is the important thing. They are two independent real numbers. They are independent, they are not depending each other. So like a comma b, okay, this is an ordered pair a comma b. Since they are ordered pair 2 comma a comma b, it feels like a feeling of a 2D plane. Okay, feeling of a 2D plane. Just like the x comma y, this has a feeling of a 2D plane, ordered pair x comma y, where x is the x coordinate and y is the y coordinate of any point. Okay, same way since AB is similar to xy things. So complex number is basically the complex number, that's why is helpful in solving the 2D geometry problem. Okay, just like we have any such geometrical problem can be solved in a multiple way. We started with simple analytical geometry. Okay, then we use the coordinate geometry to solve the problem. We also use the trigonometry to solve the problem, and we also use the vector to solve the problem. Okay, but the 2D geometry problem can also be solved using the complex number method. Okay, complex number. And obviously this is used to solve the circuit problem or other engineering problems which we study in detail, or which you study in detail in engineering particular branch, particular course, maybe electrical or electrical engineering or control system. You see the application of the complex number. But since let's discussing about the basics of the complex sense, that is the complex number, so we'll focus few of the lectures, starting few lectures discussing about the complex number. Okay, so if we talk about the notation as I discussed earlier, that z is equals to a plus ib. Where what is a is called the real part of z, and b is called the imaginary part of z. And this, again I am emphasizing that both a and b are the real numbers. They are independent, but they are the real numbers. That is important. This b and a both are real number. B is called the imaginary part of a real number. They are not the imaginary number, they are the imaginary part of the real number, whereas a is the real part of a z complex number. But a and b is a real number. That is the important thing. A and b is a real number. For example, let's say z is equals to 2 plus 3i. Okay, this is a complex number. And see, there is something called, if we have any complex number is just a, so there is only real number. This is called a pure real number. So pure real number, pure real complex number. Okay, the pure real complex number. If we have a z is equal to, let's say, IB, there is no real part. It is called a pure imaginary complex number. Pure imaginary complex number. And sometimes if we have a okay, we'll discuss that part. So basically we can say that the any complex number, if in this case if the b is 0, we'll call it pure real complex number. If a is 0, we call it pure imaginary number. Okay, what happens if z is equal to 0? Obviously z is equal to 0 means it has pure real, we can say it's a pure real number, also a pure imaginary number, because z0 can be written like this, 0 plus 0i. Okay, that means either z is equal to 0 or z is equal to 0i. So z is equal to 0 is both. We call it a pure real number or pure imaginary number. Okay. So this is the some basics notations. So let's discuss about the representation of a complex number. Okay, so let's discuss about the representation of a complex number. Representation of a complex number. So before seeing the representation of complex number, you know how the real numbers are represented. If we talk about the representation of real numbers, so basically they are represented on a number line. Okay, so let's say any number is given like this. So we have 0, 1, 2, 3, all. Let's say any root 2 is somewhere here, or minus 1, minus 2. So any real numbers can be represented on a number line. But if you talk about the representation, of a complex number, so they are represented just like the real numbers are represented on number line. Number line is nothing but a line, okay, which has the numbers, all the real numbers. Same way the complex number are represented on a plane, that is called organ plane, or we also called a complex plane. So organ plane is something similar to the Cartesian plane. So in the Cartesian plane we have the x and y axis, exactly same as the organ plane or the Cartesian plane. Only thing is we don't call x axis, we call as the horizontal axis as a real real part of z axis, and the vertical axis is called the imaginary z axis. Okay, and since conventionally we call the real part of z as x and imaginary part of z, so sometimes we also use the x and y. Okay, because conventionally the complex number written as x plus iy. Okay, that means x is the real part of z and y is the imaginary part of z. So we can replace the real part that by x and imaginary part by y, but they are different. This is the Cartesian plane and this is the organ plane or the complex plane. Okay, they are exactly same, only the method of writing is different. Okay, but the sense is same, the meaning is same. Only thing is the way we represent the complex number. So in case of Cartesian plane we represent any point, Okay, we represent any point A comma B, where in case of complex plane we represent the complex number by writing A comma IB. Essentially the way we draw the A plus IB and the way we draw the A and B exactly same. Here where somewhere is the A, here somewhere is the B, so this point is A comma B. Same here also, somewhere is the A, somewhere is the B. So this particular point here is complex number. With the way we write is a complex number. So if you have any complex number, let's say z is equals to 2 plus 3i. Okay, so how we write in the Cartesian plane, we have just a point 1 2. So in the Cartesian plane we write 1 2 1 2 3. So this is the point 2 comma 3 in a Cartesian plane. But if you talk about the representation of 2 plus 3i, that is a complex number on Argand plane or the complex plane, then what we do? We will draw we draw the Argand plane or the complex plane. They are nothing but we write a real part of z-axis and imaginary part of z-axis. So here again 1 2 1 2 3. This is the point 2 comma 3, but we write this point not as a point P as a 2 comma 3, but we write as a 2 plus 3i. So the representation of a complex number is similar to the representation of point in a Cartesian plane. Okay, and other we can say the method or the other way to represent or the complex number is a vector. Okay, so we'll see how they are represented as a vector. But we have, let's say, z is equal to a plus ib. See, you should see that this a plus ib, why I am saying that it's similar to the complex, it's similar to the vector, because a plus ib, where what is the I is just a notation to segregate the real and imaginary part. So if I is attached with any number, that number is called the imaginary part, and if I is not attached with the other number, they are called the real part. So I is basically used a notation to segregate the real and the imaginary part. Okay, it is not represented on a plane. I is, if a plus ib, we just like in the plane we see 2 plus 3i, so we represent 2 and 3, we don't represent I is the notation to segregate which is the real and which is the imaginary part. It is something similar to the vector. If you talk about the vector, let's say 2i plus 3j. So here I and j are used to segregate which is the horizontal component and which is the vertical component. But we don't represent I and j. It's just a notion that 2 has to be represented on a horizontal plane and 3 has to be represented on a vertical axis. That's all. Okay, so this is let's say this is a vector. This point is 2 comma 3 is the point, but this vector is like this. Okay, 2 plus 3, 2i plus 3j. So, and since this is similar, here we are segregating the real and here we are segregating with I with the real and imaginary part, is similar to how we segregate in vector as a horizontal component and the vertical component. Okay, so basically the complex number is also the 2D vector, we can say. It's also a vector in 2D, okay, or 2D vector. So just like if I say any, let's say vector OP is 2i plus 3j, so we represent, let's say 1 2 1 2 3. So this is point P. So this is a vector OP. Okay, in xy plane. In xy plane, they are the vector OP. Same with the, let's say z is equals to 2 plus 3i. So here 2 1 2 3 with this point, this is we write as a z. And this is the Argand plane. In the Argand plane, we represent that like this. We have the same way as we plotted the vector, same we plot as a complex number. And we can say z is equals to OP. So the better way of why I said that the complex number can also be represented vector. So we will write like this, 2 plus 3 like this. We use this notation. Okay, they're just like exactly same as the vector. So this complex number can be represented as a point, can be represented as a vector also. Okay, so just like the vector has a direction as well as the magnitude, same way the complex number z has both magnitude and the direction. Okay, so they behave exactly same as the vector. So let's say if anything z is equals to minus 2 plus 0 I, that's minus 2. So where is minus 2? Somewhere here is the minus 2. So if we represent this complex number z is equal to minus 2, we can represent like this as a vector. Okay, this is the complex number z. This is exactly same as if we want to represent any vector is equal to minus 2i. So this is same. In vector also we represent like same. So the representation of a complex number is exactly same as the vector, because vector has both magnitude and direction. Same way complex number also has a magnitude and direction. And complex number is nothing but it is represented as a vector in 2D. That's important. So only a and b, only two component, a and b, only two component is same as the vector. So basically complex number is represented as a vector in 2D. So complex number is nothing but it's a vector in 2D plane. Got it? Let's discuss about the magnitude and direction, some basics of the magnitude and direction. So if any complex number, let's say I use x and y, but don't confuse the x and y with the Cartesian plane. X is conventionally is the real part and y is conventionally as the imaginary part. So I sometimes use x and y, but this is essentially a Argand plane or the complex plane. So any complex number p is, let's say z is equal to a plus ib. So this is called the distance zob. So what is the magnitude? Magnitude is nothing but the modulus. So what is modulus? Modulus is the magnitude of complex number. Got it? So modulus is the magnitude of complex number. So as I discussed that the complex number has both magnitude and direction. Same way the modulus is called the magnitude. Okay. And what is this one? This is represented like a mod z. Magnitude of z is, and they are the distance from the point P from the O. Okay, so this is nothing but the distance OB. This is the distance P from origin. And if we clearly observe that this is A comma B, so this is essentially a B, this is essentially a A. So the magnitude is A square plus B square root. So we can say that the modulus of Z is A square plus B square root. See, z is, even though z is a complex number, but mod z is pure, because mod z is a and b are the pure real numbers. Okay, so square, adding and then taking root again, they remain to be a real number only. So mod z or modulus of z is a pure real number. Okay, it's a pure real number, and one important thing is they are non-negative. They are not positive. They are non-negative number. So modulus is a purely real non-negative number. Okay. So modulus is the easy part, just a distance. The little bit complicated part is the direction, the argument. Okay. So argument. What is argument? So argument is the any complex number somewhere here p, z is equal to a plus ib, there theta. So what is the argument of z? So we will say that this theta is the argument of z. We represent it like this. Theta is the argument of z. So what is this theta? Theta is the angle the vector OP. The angle the vector OP makes with the positive direction of x-axis in the anti-clockwise direction. That is important. See, as we do in the trigonometry, if we are measuring any angle in the anti-clockwise sense, this is a positive angle. Whereas if we measure angle in a clockwise, they are a negative angle. Okay. But they are measured, important thing, they are measured from with respect to the x-axis, positive direction of the x-axis. We can't measure from y or y negative x-axis. Angle is always measured with respect to the positive direction of x-axis. And if it is clockwise, it's a negative. If it is anti-clockwise, it's a positive. So one crude notation, not exact, one crude where tan theta is argument of z, and since we know that this distance is the b, this distance is the a, so I can say that the tan theta is b by a. But don't believe on directly tan theta is equal to b by a is the direction or the argument. We have to use some little bit we have to use little bit the knowledge of which quadrant our complex number lies. Then only we can write the exact value of argument of any complex number. So essentially I am ending the class here. I will start in the direction or something, but before ending we can say that a complex number is treated as a vector. That is important. Why we treat as a vector? So vector in 2D basically. So basically vector has a magnitude and the direction. Same with the complex number has a magnitude which is called the modulus, and it has a direction which is called the argument. Okay, so what I mean to say that any complex number, let's say this is real and imaginary axis, and we have any complex number is here. So this, what is this any complex number? Let's say this angle is let's say 5 pi upon 3. So the argument of z is 5 pi by 3. By the way, we can also measure in the clockwise sense also. That is a minus, since it's in clockwise sense, it's a minus pi by 3. So the argument of that is also minus pi by 3. In fact, we can also say that, let's say this is goes like this and this also. So the argument of that is also we can write in general as 2 and pi plus 5 pi by 3. Okay, and same way we can measure in the clockwise sense. So then in this case it will be minus 2 and pi plus pi by 3, but since the clockwise sense we'll have a negative here. Okay, so there are infinite arguments are possible. Important thing is argument can be can have a infinite values. Okay, so but there is something called a principal argument. So distinguish between the argument, we have the principal argument. We use the word principal argument. Principal argument. What is principal argument? They are represented sometimes like a capital R, the principal argument. The principal argument restrict the values of argument between minus pi to pi. Okay. Now this it will restrict the infinite values of argument. So it will have a either basically it has a minus pi to 0 and then 0 to pi. So it has a value minus pi 0 means like this 0 and this one. This is from the minus pi to 0. Okay, and the other is 0 to pi. So 0 to pi. So this will cover, whereas minus pi, so minus pi has an open bracket whereas pi has a closed bracket. So if the positive x-axis it has a capital pi, will not say minus pi. The argument of this any values on the x on the negative x-axis has a capital pi, not the minus pi. Okay, so principal argument essentially now able to capture all the quadrant, first, second, third, fourth quadrant. First quadrant or second quadrant can be represented from first quadrant 0 to pi, second quadrant is from first quadrant is 0 to pi by 2, and the second quadrant, first quadrant is 0 to pi by 2, and the second quadrant is pi by 2 to pi. Whereas if you want a third quadrant, fourth quadrant, so third quadrant is, so basically I can say that the first quadrant is 0 to pi by 2, second quadrant we can have a pi by 2 to pi. The third quadrant, now we measure anti-clockwise, clockwise. Third quadrant is, we can say minus pi to minus pi by 2, and the fourth quadrant is 0 to minus pi by 2. Okay, so we can see first and second quadrant measure in the anti-clockwise sense, where third and fourth measure in the clockwise sense. Okay, so for example, let's say any complex number has 0 z is equal to minus 5. If I talk about what is the modulus of z, 5. If I talk about the argument of z, what is the argument of z? So argument of z is, if you look at the thing, somewhere minus 5 is here, so it is here. So if you want to measure this particular vector or the complex number is like this, and its direction is obviously here will this argument that is pi, will not say minus pi, will not measure from this one, because minus pi has the open brackets, we can't have a minus pi, we can have only pi. Similarly, if let's say talk about the any z is equals to I, so I means 1, so basically it means we have somewhere is the 1 or 0 plus I, and this basically complex number I is represented like this, and its direction is like this. So the argument of z is, or we can say principal argument, let's say capital, principal argument of z is pi by 2. Okay, so essentially the argument of z means the general value of argument, general value of argument we can say, general value of direction or the argument, whereas capital A R means we can say it's a principal value, principal value of argument, principal value of argument. Okay, that basically it has the values from minus pi to pi. One important thing is argument of 0. So चलो इसको लिख लेते हैं, will next time, but let's say argument of 0. What is 0? Z is equal to 0 means 0 plus I 0. So what is the modulus 0? Modulus is 0, but what is the argument of 0? Okay, or principal argument or general argument of 0 is basically we say not defined, not defined. Argument of 0 is not defined. See, just like in the any vector, let's say vector is 0i plus 0j. The magnitude of this is 0, but if I talk about the direction of a, we write 0 by 0, 10. So basically how to write is 10 inverse 0 by 0, no, something. So 0 by 0 is not defined, so that's why the direction is not defined. So 0 is a complex number whose magnitude is 0 but direction is undefined. Got it? So just like any we say vector OA is equal to 0. By the way, vector we write 0 as a vector here. So OA is 0. So its magnitude is, obviously its magnitude that is 0A is equal to 0, but direction is undefined or not defined. Similarly, if any complex number 0, so again the magnitude or that is called a modulus. The modulus in complex number mod z is 0, where the direction or the argument, direction means the argument of z if 0 is not defined. Okay. So essentially I am ending here with the final notation that if theta is argument of z, we can note down this, if the theta is argument of z, then 2n pi plus theta where n is any integer is the general argument, because it has infinite values. Whereas if the value of argument, if the value of argument lies in open bracket minus pi to close bracket pi, is called the principal value of argument. Okay.